In this video, we are going to introduce sampling distribution. Sample statistics are estimates. We not only need to know how to calculate them given a sample of data, but also need to know how good of an estimate it gives us. So what would be a good estimate? A good estimate would be one that falls close to the true population parameter that we are trying to estimate. How do we determine how close a sample statistic is likely to fall to a population parameter? The answer is we look at the sampling distribution. Every possible random sample can result in a different sample statistic being calculated. This sentence is well explained by this box plot here. This is sample 1, and this is sample 2. Statistics from sample 1 and sample 2 are not identical. Let's say you have a population of data that had the following x values 1, 2, 3, 4, 5, and we want to pull a random sample of size 2. Notice that the sample mean calculated will depend on which of the values is randomly sampled. In the first sample, we have value 1 and 2, so the sample mean is calculated as the average of 1 and 2. For the second sample, we have value 1 and 3, so the sample mean is calculated as the average of 1 and 3. And so on and so forth for all samples we have here. There were 10 different samples possible for the population that consist of 5 data values. It means, at the most, you can have 10 combinations of two numbers sampled from 1, 2, 3, 4, 5. The order of sample values does not matter. This means if you have first number to be 1, second number to be 2, or you have first number equal 2, second number equal 1, these samples equals to each other. 10 sample means you have one possible combination here, and this is the second possible combination. Your total, you have 10 possible combinations of values sampled from 1, 2, 3, 4, 5. This is an extremely important concept to keep in mind. The values of the sample mean will vary for each possible sample taken. Note that some of these values could be considered much better estimates than others. The population mean, mu equals 3, which is the average of all the data in the population. 2 of the sample means were calculated as 3, so these we could consider were perfect estimates. However, the other sample means were not exactly the same as the true parameter values was needed to estimate. Note that one sample had a mean of 1.5 and the other 4.5, so these estimates would not be considered as good. How good the estimate will be will depend on which values are sampled, but remember that we are randomly sampling from the population, so we can control this. This is just a small example. Think about how many different possible samples are possible if you are looking at the population with 50 data values and you want to pull a sample of size 10. There are over 10 billion different possible sample combinations. This gives us the basic knowledge we need to understand the sampling distributions. For the brief example above, we would look at the graph of the possible sample means calculated. Notice the difference now is that the x-axis represents not what the data itself looks like. This is not x, but what the sample statistics looks like. So again, it's obvious. The x-axis represents sample mean. What does the sampling distribution tell us? It tells us how much variability there can be in a sample statistic. It also helps us predict how close a statistic falls to the parameter it is estimating. Here are some useful notes of sampling distributions. Results of the sampling distribution are only appropriate for a randomly selected sample. In practice, we generally only pull one sample from the population and use one sample statistic instead of pulling a lot of different samples. Up to this point, we have learned 3 different distributions that all show different information. The first one is population distribution. So population distribution is the distribution of the population data. In other words, it is all data values from the entire population. This is the distribution that the sample is plotted from. Values from this distribution, either center or variability, are called parameters and are unknown. By taking a sample, we hope to make predictions of the unknown parameters. The second distribution we have learned is called data distribution. It is the distribution of data taken from the sample, and it is the most common one used in practice. Values we get from this sample are called statistics. With random sampling, the larger the sample size, the closer the statistic will resemble the parameters they are estimating. This distribution will be different for each sample taken. The last concept is sampling distribution. It is the distribution of the statistic. The value of the statistic will vary from sample to sample, so we get a distribution of all possible values. With random sampling, the sampling distribution provides probabilities of all possible values of a statistic. The sampling distribution holds the key for telling us how close a sample statistic falls to the corresponding unknown parameter.